In this buffer problem for 1982, obviously, in the beginning of the question, it says we've got a buffer solution, so we have to consider it as a buffer. But the other evidence that it's a buffer is shown in that the formic acid, and there's our formic acid with the formate ion, and then the salt of that formate ion, sodium formate, is also given. Be on the lookout for those, where that same ion is present in both the acid and the salt of that acid, because that's a dead giveaway that we're looking at a buffer question. I mean, obviously there are a lot of other questions that could come with any weak acid problem or rice table in general, or just a question relating to acid-base chemistry in the first place. But for this one, we've definitely got a buffer for a couple of good reasons. So when they ask us to calculate the pH for A, remember we're going to use that modified Henderson-Hasselbalch equation. That's helpful for studying buffers without having to bother as much with logs. And that has to do with hydrogen ion is equal to the Ka of the acid times that acid-base ratio. So the molarity of the acid divided by the molarity of its conjugate base. And those are both molarities or both moles. So remember, in our brackets here, we can use molarities as always, or because both the acid and the base ions are occupying the same solution with the same volume, we can kind of leave the volumes out of our molarities and just put moles in to those two places in the equation. So that can save us a lot of trouble. In this question, that's the way we could do it because it gives us moles. It's also a simple solution, being that it's 1 liter, so things are relatively straightforward anyway. But we'll solve this one using moles, so you get used to the idea that because volume is consistent between both the acid and the base solutions, you can kind of just leave it out and plug moles right into those boxes. So for this particular problem, we've got a Ka for our acid given here, 1.8 times 10 to the negative 4. And then we've got both the acid and the base given in moles in 1 liter. So we're going to use those just as moles. So here's the acid. We have 0.4 moles of acid. And we have 0.6 moles of its conjugate base dissolved into 1 liter of solution. So this is 0.4 moles, and this is 0.6 moles. Again, molarities would certainly work there. Obviously, that's what the equation says, but we can use it as moles because the volume is constant. Plug this in your calculator, and you should get 1.2 times 10 to the negative 4th molar. That's our H concentration. So question A wants pH. That's obviously not quite the same thing, but we can quickly get there from there. pH is inverse log of our H concentration, which we just found to be 1.2 times 10 to the negative 4 molar. And that gives us a pH real close to 4 of 3.92. Remember the rounding rules for significant figures with doing log or undoing log, that if you're operating with log, the significant figures in your value here, 1.2 times 10 to the negative 4th, 2 significant figures means we should have 2 decimal places in our answer for pH, which we do. So 3.92 for our pH here. All right, in question B, if 100 milliliters of this buffer solution, so again, they're talking about the buffer we just prepared up here. So we're taking 100 milliliters out of that 1 liter sample that you've prepared. You're pouring it into another container. You've diluted that now down to 1 liter. So we've taken that buffered solution, we pulled a little bit out, and we brought that up to a full volume of 1 liter. The pH does not change, it claims here. Discuss why the pH remains constant. So in other words, why does watering down this buffer not affect the pH? Well, it goes back to the math you just did. I mean, look at the equation that you just solved. To find the pH, we found the hydrogen ion concentration. To find that, we used Ka, and we used the moles of acid over the moles of base. Well, in this case, if we're finding pH to be constant, as they're claiming here, the pH remains constant, it's due to 2 factors. One, the Ka doesn't change. The Ka for an acid is a constant by its very name, okay? Regardless of how watered down or concentrated that particular acid is, the Ka is a constant for that acid. So by adding more water or watering down this particular buffer, that doesn't change the Ka value at all, so that's not going to change. And then the ratio of acid to base doesn't change here either, right? So if we're watering down this solution from the amounts that we had in the last problem, which were 0.4 and 0.6, basically in this watering down, we would take this down by a factor of 10, right? We're pulling out 1/10 of that solution, 100 milliliters, and then we're watering it down with water to dilute it. So you're essentially going to have, instead, if we redid the math for part B, we would have 1/10 as much of this, and 1/10 as much of this, which would be 0.04 over 0.06. Well, you can run the math yourself, but if diluting it by a factor of 10 dilutes both of them proportionally, then the ratio would stay the same. Okay, 0.4 over 0.6 is basically 2/3. And so if we plug this into our math, we'd still get 1.2 times 10 to the negative fourth for our hydrogen concentration, and we'd still get the same pH value when we did inverse log of that. So in the end, changing volume, increasing volume, or you could say watering down the buffer, increasing the volume, it does not affect either of the two important factors that determine pH. Okay, so either the Ka nor does not affect either or, pardon me, better go with proper grammar here, okay, or the ratio of acid to base. So hydrogen ion would stay the same. And therefore pH is still the same. And we'd say still sit at about 3.92. Now that's kind of a concise description, right? So remember, what determines pH? If you don't know how to answer this question, you're kind of doubting yourself. Like, think about it. What determines pH? Well, in this scenario, we'd still find pH the same way. It's still a buffered solution, so we'd still use our same modified Henderson-Hasselbalch equation. And the things that go into calculate hydrogen ion haven't changed. Therefore, the hydrogen ion molarity hasn't changed either. Now, one thing should be noted, diluting a buffer, like we've done here, does have an effect. It doesn't change pH necessarily, but it does have an effect in that watering down a buffer would give it less capacity to act as a buffer. What that means is, as you add an acid or a base to that solution, after you've watered it down, the ions that are doing the buffering, which are the formic acid and the formate ion, the conjugate base of that acid, those that are doing the buffering, those particles that are doing the buffering action of this solution, have to act over a greater volume of solution. And so they can do the same thing, but because they're spread out through a greater volume, their capacity to act as buffers is sort of reduced. So think about it. If I give, let's say, some number of law enforcement officials a certain city to cover, they can cover it safely, they can protect that city safely. If we suddenly take that same number of law enforcement officers and spread them over a city 10 times the size, they're still doing the same job they were doing before, but now they have to protect and defend a larger space against the invasion of, say, criminals or something. And so in the case of a buffer, you're taking the same actors, the acid and base ions, and spraying them out over a much larger solution. They're still going to do the same thing, but they're going to be a little bit less able to protect as much volume as well as they could in a more concentrated form. So they're doing the same job. Their job and description is still the same, but their effectiveness over that larger space would be reduced just by the fact that they've been kind of diluted by spreading them out. So avoid descriptions like police officers and things on any kind of an AP exam question, but it helps you think about why a buffer's capacity is reduced when it's diluted. So for question C, we are taking an acid now in question C and adding it to 100 milliliters of the original buffer solution. So you're going back to the very first mixture that we made, where we had 0.4 moles and 0.6 moles of each of the acid and conjugate base in the solution. And we're adding 5 milliliters of an acid to that. So in question C, 5 milliliters of 1 molar hydrochloric acid. Adding a strong acid to a buffer is going to potentially reduce the pH, right? So we're predicting with part C that in the end, calculating the hydrogen ion, this should be greater than it was at the beginning of our problem. So our original hydrogen ion was 1.2 times 10 to the negative 4. We should find that the hydrogen ion concentration is greater now once this acid does its work. So our answer to C in the end, we would expect, comparing it to this, should be somewhat greater. Okay, so we'll say greater than our answer A. That's our prediction, at least up front. Because we're adding an acid to the solution, our hydrogen ion concentration should be greater. They aren't asking us to find pH, so we can compare that as well. So what are we doing here? For C, we're still in a buffer, and we still want to use our same equation. So to find our H3O, or hydrogen ion, they're kind of interchangeable here. To find our H3O concentration, we're still going to use the same equation that we used earlier up here. but we're going to add in the acid to show its effect in the ratio of acid to base. So the Ka is still the same, 1.8 times 10 to the negative 4. Our ratio of acid to base, however, has been changed because when we add an acid like HCl to the solution, that acid comes in and contributes more to the acid and at the same time cancels out some of the base equivalently. Adding an acid to the solution is going to both act as an addition to the acid side and a subtraction to the base side. You're bringing in acid reinforcements. And in doing that, you're strengthening the acid side of the ratio and you're weakening the base side of the ratio. The question is how many moles? So we were working in moles before. We need to figure out how many moles of HCl, or rather H from the HCl, are being added. Well, 5 milliliters, right, is 0.005 liters, and it's a 1 molar solution. So how many moles of acid are we talking about here? Well, from this solution, 0.005, and I'm going to keep the sig figs on there, liters, times a 1 molar solution. So that's 1 mole per liter, would be 0.005 moles of hydrogen that are being added by the strong acid. Okay? And again, I'm using hydrogen and hydronium interchangeably here. You're welcome to do that as well, as long as you know they're the same thing. Okay, that works okay. But that additional acid, okay, those additional acid ions need to be factored into the numerator of our ratio because that's where the acid is. So those are being added on the acid side of the ratio. They're being sort of subtracted because they neutralize some of the base as the buffer action takes over. Some of those base particles are consumed. And so as we work this out, we're going to be contributing more acid particles by adding an acid, which makes sense. And at the same time, we're going to be neutralizing some of the base particles on the bottom. So the extra 0.005 moles is added to the acid side on the top. So we now have 0.0, pardon me. Oh, I was correct after all. Hold on just one second. So because we're working with 100 milliliters of the original solution, we don't have a full 0.4 moles of our acid. We have a tenth of that, right? Because we're working with 0.1 liters. So just to kind of pull that apart for us, 100 milliliters would be 0.1 liters. Our original acid was 0.4 moles per liter. So this is our formic acid. Keep in mind the original acid we were looking at here in our first calculation was the hydrochloric addition. So those are the acid moles, the acid ion moles being added to the solution. The original number of moles of acid would be, if we multiply this out, 0.040 moles of hydrogen ion already present, acid present. And we'd be looking at, for our bottom, formate ion in our sodium formate conjugate base. Again, we're using 100 milliliters, so 0.1 liters times the molarity there, which was 0.6. That's going to give us 0.06 moles of our base. So if we put all this into our Henderson-Hasselbalch, modified Henderson-Hasselbalch equation, on the top we have an acid of 0.04 moles. That's the original amount here. Okay. And then we're adding to that 0.005 moles. Okay, that's the addition here. It acts as reinforcing or adding to the numerator. At the same time, on the bottom of our equation, we have 0.060 moles of base. So that's this amount here, the original amount of base. And because we're adding an acid, some of that is going to be neutralized. Okay, when we add this acid to it from the outside that we consider sort of an invader, it's going to use some of this base, neutralize some of this base, and so we subtract from it. They're 1-to-1 in our equation ratio, so we subtract from it 0.005 moles there. So when we add an acid, it reinforces on the top there, and it reduces or subtracts from the bottom on the base part of the denominator in our equation. So I'm going to clear those arrows back out just for clutter's sake. So it's kind of a bigger ratio now, but I'm going to just simplify that down. We got 1.8 times 10 to the negative 4. That's still our Ka value. In our ratio now, we have 0.045 because we've added on the top. And by subtracting on the bottom, we now have 0.055. Okay, we subtract those out. Now you could go ahead and just punch all that in from the beginning. I just want to show you here that in comparison to before, where it was basically a 4-to-6 ratio in our original equation on part A, we have now more than 4 on the top and less than 6 on the bottom. Now, I'm simplifying things by not talking about the decimal places, right? But by diluting it down, we said before, the ratio wouldn't change. Now we've added an acid, so we have more than the original 0.04 on the top. We have less than 0.06 on the bottom. So the acid side, the numerator, has taken a little bit of an edge and gained an advantage. So if I plug all this into my calculator in the end, I should get 1.5 times 10 to the negative 4 molar. Now remember what that is. That's way back here. That's my hydrogen ion concentration. Okay? So my hydrogen ion concentration has increased. We said before it should, in the end, our answer here should be greater than, greater than the original amount. So there was our first hydrogen ion concentration, 1.2 times 10 to the negative 4. By adding some acid, it would make sense that our hydrogen ion concentration has increased, and it has to 1.5 times 10 to the negative 4. Now that's our answer for C. We're not asked to find pH. We could. We would expect that our pH here would be slightly less, right, than 3.92. More acidic, so slightly less than 3.92. But for the sake of figuring it out, let's just quickly do that. So inverse log of 1.5 times 10 to the negative 4. And we get a pH of 3.82. So the pH has dropped by 1/10 of a unit. Not much, right? Well, that's the whole point. This is a buffered solution. We would expect that using a buffer would mean the pH will change, but not nearly as much as we anticipated to in a solution if the buffer wasn't there to do that action. By adding a strong acid, as we've done here in part C, that should have affected the pH much, much more. We could do the math and figure it out, probably on the order of a full pH unit or even more in this situation. So in the case here, it's buffered it down to where it only changed the pH by about 1/10 of a pH unit, which means the pH has been stabilized and isn't being affected nearly as much as we would have expected for that acid being added, which makes good sense. Now, in final question in part D, okay, I'm going to pause here and I'm going to move that question down so we can work with the question a little closer by. So excuse me while I pause. I'm going to just rearrange things here. Okay, so for part D, we've got a whole different scenario here. We're not using a buffer here anymore. So pay attention to the questions when they do this. They're giving you a scenario, they're giving you some background information, they're giving you the Ka value for formic acid, and then at the end, they switch gears completely and don't ask you to work with the buffer anymore at all, which may or may not confuse you if you catch it in the moment. But at this point, there isn't any sodium formate in our solution, at least not initially. We're about to make some, as it turns out, but we'll talk about that as we go. So we're talking here about an acid solution, so 2 molar formic acid, and we have 800 milliliters of it. To that, they're adding 200 milliliters of a 4.8 molar sodium hydroxide. Now, of course, in the end, what's going to happen? Well, we want to look at the equation, maybe consider what's going to go on here. Our equation for the reaction would be HCOOH, okay, plus our sodium hydroxide. This is an acid-base neutralization. So we're going to get out the other side water, which we're not usually that interested in. Okay, and we're going to get our sodium formate ion. Now, the way they usually write those, you're going to see, is a little different than what we learn about when we're learning nomenclature in first year chemistry. We usually would put the sodium up front, but they've been writing it like this throughout the problem, and so we'll stick with that. So you can kind of see here, this is the conjugate base salt, right? So this is that salt of our formate ion from the original acid over here. So acid and strong base, which is usually the case in a titration. We'll have a weak acid and a strong base, or vice versa. And then over here on this side, we have what would be acting as a basic salt. So it contains the conjugate base along with the sodium, which makes it a basic salt, and then water. So that's the equation of what's going on. This kind of gives you an idea of what's going to be present in the solution potentially at the end, the different pieces that might actually be there. Now, in this case, have we reached titration? Have we completely neutralized the acid? That's an important question to consider. So let's set up our rice table here. We've got our reaction, so the initial amounts, change, and ending. We want to find out if the acid's been neutralized, and if so, how completely. If not, how much of it's left over, and that sort of thing. So how many moles, or we could look at it in terms of molarity, in a rice table like this, because we know eventually we might want to consider moles to fill in our Henderson-Hasselbalch equation. It's probably not a bad idea to work in moles from the very start because stoichiometry is a little simpler when we think about it in moles. So how many moles have we got? Well, for our acid, we have 0.8 liters and a 2 molar solution. So that's 1.6 moles of the acid. I'm going to put that in down here, 1.6 moles. For the base, we have a 0.2 moles, or sorry, I'm sorry, 0.2 liters times 4.8 moles per liter. And that comes out to be 0.96 moles of our base. Put that in here. Now, since these are, as often is the case in these kind of questions, a 1-to-1 ratio, we can tell that the acid is excess here. The base will be completely used by this reaction, but not all of the acid will be completely used. These, not water, we're not interested in as always. We can kind of blank them out. The base hasn't begun to form yet. So as this happens, all of the base will be used up, and an equal amount of the acid will be used up. And on the other side, that same amount of salt will be formed. Right? So in the end, we have left over then 0.64 moles of our acid. This is gone. It 0 there, so we're not quite considering it the same as our water. And then we have 0.96 moles of our salt, our conjugate base. Those are the two important players, right? As we look into solving for our Henderson-Hasselbalch, we want some acid and its conjugate base salt. That's what we've got. So they set us up quite nicely. From here, we're practically done. As we don't need to work with volume, we've combined these into 1 liter anyway, right? 800 milliliters plus 200 milliliters, real simple, we got 1 liter. But we can still work with moles, so we'll stick with that just to be consistent here. And in this problem, we're still looking to solve for our hydrogen ion or hydronium ion. Feel free to treat those interchangeably. Ka is still 1.8 times 10 to the negative 4. And our ratio of acid to base here, the acid from our Rice table, we want the bottom line, right? So 0.64 moles of our acid. And our base here, conjugate base salt, 0.96. Okay, there's our ratio. Now the base on the bottom is in greater amounts here, as we've seen in places throughout the problem. So again, we're going to get an answer that sort of reflects that. But in the end, we'll punch this into my calculator, and my final answer here, 1.2 times 10 to the negative 4 molar for my hydrogen ion concentration, and that's what they want. Okay, they aren't looking for pH here again. So what was different about this question? Well, we had to sort of make the salt. In the beginning, for the first several parts of this problem, we had the acid and we had the salt already there. We were manipulating those concentrations by adding an acid in part C, but we already had some of them there. It was a buffer solution in advance. Right? In this case, imagine this is along the lines of a titration. So you're starting with an acid, you're adding a base to it. This is in large quantities for a titration, but you kind of get the idea that we're starting with some acid, 800 milliliters. We're adding some base to it and titrating or neutralizing some part of the acid. We haven't titrated it completely. Okay? We've gone past the point of the half equivalence. And I know that because if we were at the half equivalence point, half of the acid would have been neutralized, right? So the half equivalence point, kind of as a side note here, half equivalence point would have been when half of this original amount of acid had been used. So if this bottom value was, say, 0.8 moles, and we would have 0.8 moles of the salt, that would be the half equivalence, right? So if we can kind of picture this, it doesn't hurt to do this. It's not part of this particular problem, but it doesn't hurt to do this. Think about this as a titration problem. We just started out with some acid pH, so down here in the lower ranges somewhere, and we'd have a titration curve that would look something like this, right? The half equivalence point would be, we're going to suspect kind of right in here someplace, right? That would be the half equivalence. In this problem, we've gone a little bit past the half equivalence, so probably somewhere kind of right in this range. And we've gone past it, but we haven't lost the buffering range. We haven't spiked our pH. We haven't seen a great change in our H3O concentration. At the half equivalence point, that would have been the hydrogen ion concentration right in here, and our pH that we originally found. At this point, we've gone a little bit past that by adding a little bit more than that equal amount of the base. So slightly more than half the acid has been titrated. We've gone slightly past the half equivalence point, and we're on our way to that equivalence eventually. We could estimate and figure out from there how many milliliters of acid it would take, or other base it would take, to reach that the full equivalence point. That's not part of this particular question, so we won't get into that on this one. Hopefully that made some sense. We'll be coming back with question for 1993 and for 1996 in the next videos. Thanks for watching.